Welcome to Monochemistry. Today we're going to look at how to solve weak acid equilibrium problems. For example, like the one I have here. And the one I have here is a typical weak acid equilibrium problem where you're asked to solve for the pH of a weak acid. So the question says, what is the pH of a 0.0100 molar solution of a weak acid, HX, if the Ka, or the equilibrium constant of the acid, is 8.1 times 10 to the negative 7. So step 1, and you should take notes on this, make sure you know how to do it. Step 1 is to write the dissociation equation for the acid, which I have done right here. Step 2 is to create an ice table and to fill it in. Okay, so the first thing I'm going to do is I'm going to write the value for the concentration of the acid given and put in zeros on the product side, because initially there would be no H plus or X minus. However, over time there's going to be a change. The initial concentration of the acid is going to go down by some factor, minus X, and the initial concentrations of the H plus and X minus are going to increase by some factor, plus X. In this case, the coefficient of X is 1. And the reason that is because for every 1 mole of HX, I get 1 mole of H plus and 1 mole of X minus. Remember, the coefficients are going to give, of the actual chemicals in the reaction, are going to give us the coefficients of X in the ice table. And in this case, they're all 1. Okay, so down here, what I'm going to do, step 3, is to do the approximation rule. Remember that when we're dealing with weak acids, any weak concentrations of anything really, any weak reactions, where the reaction itself favors the reactants and not the products, we can use the approximation rule to basically to figure out if X is significant compared to the initial concentration of whatever we're using, in this case the acid. So if I divide the concentration of HX by the Ka value, and I get a value that is greater than 500, which in this case I do. I think I get 24,000. It's a big number. So I get a really big number. If that happens, like it does in this case, then I can assume that this X here is actually negligible. It's not important compared to the number that was given here. So at equilibrium, the amount of HX is still basically, no pun intended, going to be the same as it was to start with. And of course my value here is going to be X, and my value here is going to be X. Okay, so that's step 1. Step 2 is to do your ice table. Step 3 is to, before you finish the ice table, to do the approximation rule and check it. And hopefully it's greater than 500, because if it's greater than 500, we don't have to do a quadratic. Step 3 is to fill in this data from this part right here into our Ka equation. So let's go to do that. Remember that our Ka expression is going to be equal to the concentration of the products raised to their coefficients divided by the concentration of the reactants raised to their coefficients. In this case, concentration of H plus times the concentration of X minus, all divided by the concentration of HX, the original acid. Therefore, substituting the numbers that were given in the question, I have 8.1 times 10 to the negative 7 for the Ka value. If I look at my ice table, I have X and X for each of these, and I have 0.100 for my concentration of HX. And so if I do, through the magic, like I say, the magic of math, through the magic of math, algebra, if I rearrange the equation to solve for X, I end up with X is equal to the square root of 8.1 times 10 to the negative 7 multiplied by 0.100. And then, of course, I'm going to take the square root of that. And what I get is, go ahead and try it. And when you're ready, move on to the next page. Because remember, the question didn't want the value of X. It wanted the pH. Okay, so once you have that value, you're ready to move on to the next screen. So go ahead and do that in your calculator. Now we're ready to calculate the pH. remember that the pH is equal to minus the log of the H plus concentration, but Mr. Monahan, we don't have the H plus concentration. Well, yes you do, because X, as it turns out, is also equal to the H plus concentration. And now that you've solved for X, which by the way should have given you 9.0 times 10 to the negative 5, you can now find the pH. And the pH, as calculated, when you do it in your calculator, is 4.0. Okay, so even a weak acid like this one still gives us a pH of 4.0. That, in a nutshell, is how you solve a pH question using weak acid equilibrium.